Yeah, so welcome to the fundamentals of computer vision. Just like recap some of the stuff that we have already mentioned earlier, the geometric camera calibration, and assuming that I'm giving you these images and I'm asking you estimate the exact position of the photographer. Where is exactly the photographer when he or she took already this particular picture? And we said that, okay, given a set of matched points, for example, in the 3D space and in the image. So now you know this, you know that. I need this, which is the pose estimate. I need this P. So we will use, as we already mentioned earlier, the perspective camera model for pose estimation. We need to get this P. But the question is, how we can get this information from? How we can get this matched information? We already also mentioned that we will have a shape like that, which we already knew in advance, all of the parameters in the X and Y and Z. We know exactly in the real world object, where is exactly the coordinates, what is the distance, and so on and so forth. And then we know the image and we know the distance, and then we'll do like this map to this point map to this point map to this, and so on and so forth. And then we will get the P. So this is like the points in the world. These are the points in my image. And then please get P. Later on, we'll understand that there is, of course, like a shift with errors here. So it might, the point is exactly here, but the projection is here, or the other way around. The point is exactly here, but the projection is here. But this, we'll speak about that a little bit later. But just for now, we have points, that is, we exactly know in advance where is the location, and we know like the location in this 2D image, and then please get the P. So this just like remind us with the homography estimation. It's exactly the same things. We have this, we have that, and we need to get this. If you remember with the homography, the only difference that we had earlier, 8 degrees of freedom, but now we have like more degree of freedoms. And we showed you last time how we can play with this degree of freedom according like to a change that we can do in each of these matrix elements. If you remember from the homography, how did I get relation between this X, Y, and Z and the other X, Y, and Z? If you remember that we have used a SIFT descriptor. And with this descriptor, a match, the descriptor will tell me that this is correspond to that, this is correspond to that, this is correspond to that. The descriptor will actually tell me that. And we have already also mentioned at that time that this descriptor might not always give me the correct solution, and I will be able to detect the false alarm signals by using ransack. However, this matches is coming from the descriptor or the SIFT descriptor, for instance. Here, I will get these two X's by what? As I just showed you. I know an object, I know exactly where are the locations in the world space, take the image, know exactly, and do this match to this to match to this, and then from these correspondence being points, I should be able to get the P. So this gives us an indication that hopefully we'll go through the very approximate step to what we did earlier in the homography. The only difference is just like the shape of the matrix and some other small stuff. So we can write this whole row as a P1 vector transpose. So P1 is equal to P1 small, P2 small, P3 small, P4 small. So P1 transpose will be here. The same with this, the same with that. And I will call all of this as an example vector X, for instance. If I were to ask you how I can get the heterogeneous coordinates. So now this guy right now is X dash, Y dash. And this will be X, Y, and Z. How I can get this X dash and Y dash? Of course, I know that I will, in order to get something like this, of course, this means that this is X divided by Z, Y divided by Z, and this here, the 1, and then I will just take this, correct? Which I will do exactly the same by multiplication with this guy and divide by the third term. Yes? So the left I will divide by the third term, and also the right I should be able to do exactly the same. And this is what it is. The x dash, which is the first one, will be this first one multiplied by x, P1 transpose multiplied by x, divide by the third one. The third one is P3 transpose multiplied by x. Does make sense? The same exactly apply for y dash. Y dash will be what? Y dash, which was here, y over z. It will be this multiplied by that, divide by the last term. So P2 transpose multiplied by x, divide by the last term, which is P3 transpose multiplied by x. But unfortunately, this is just shows a nonlinear relation between coordinates. How we can make these relations linear? We will do a little bit of algebraic trick, as you can see. So again, this is what we had from the previous slides. We just do cross multiplication, cross multiplication. If you do this cross multiplication, P2 transpose x multiplied by 1 minus y dash multiplied by the P3 transpose x will give me 0. The same will do it here. So I have this equation and I have this equation. If I have these equations, you should directly think about the matrix shape. I would like to allocate these in a matrix, because ultimately at the end, if you remember from the homography, we end up with a multiplied by x equals 0. And then we solve it for that, yes, for the variable that we need to solve. We solve it for x, correct? We are trying to target exactly the same. So we would like to allocate this in a matrix form. So now we have this. How do we proceed? Matrix form. If you do the math, you have like the variables P1, P2, P3, and just see like what is multiplied by P1, what is multiplied by P1 here is this one, x, but this is P1 transpose, so this will be x transpose. P2, from the very beginning, from this one, there is nothing between P2, so that's why it is 0. P3, what is multiplied by P3? It is x dash, but it is transpose, so I will do the x transpose as a vector. X dash is just point, so it will not make any difference. I don't have to do the transpose. You can do the same with this one, and you will get this matrix. Okay, so now I have created the matrix. How I can proceed? If you recall from the homography, we have proceeded earlier by just adding the points. So this, a matrix form, I will apply this for 0.1 to 0.1 matches. I will apply this for 0.2 to 0.2 matches, 0.3 to 0.3 matches. And how many equations I should take, or how many points, or how many correspondence I should take? I should take the number of points that will satisfy my degree of freedom. So let's say I have an 11 degree of freedom. So I need how many points? 6. Yes, because 6 multiplied by 2 is 12. 5 multiplied by 2 is 10. So 10 will not be sufficient. So I need 11 or more. So that's why I have to take 6 points. So basically, for n points, I may take 6 points, as an example. If you have like another problem that it just has like 1 degree of freedom or 2 degree of freedoms, just 1 point, and so on and so forth. As you can see from here, that a multiplied by x equal to 0. The same exact thing that we have arrived in homography. So just keep repeating the same exact thing. How we will solve for x, which is basically p. We need to get p. How we can solve for that? Magic, SVD. We'll use that always, the SVD, singular value decomposition. How we can do that? We have spent like, I think, a considerable amount of time to review that lecture, that in order to get something like that, we have derived a certain particular way to do this. But just like at the end, I'm telling you that the solution for that x is the column of the V corresponding to the smallest singular value decomposition A transpose A, because we have already proved that A transpose A is V, let's say like the diagonal matrix V transpose. And from that, we conclude that V is the eigenvector of A transpose A. And this is the eigenvectors, which relate by sigma square, by the way, to the another sigma, which is this. But the bottom line here, that V is the eigenvectors. So with this many eigenvectors, which one I should choose? I am telling you that I solve this problem by minimizing this guy, subject to this guy equal to 1. So I would like to minimize this one. So if I would like to minimize this one, I should take the eigenvector that is corresponding to the smallest eigenvalue, which ideally will be 0, but practically it will not be 0. It will be something very, very small. That's why I will take this particular eigenvector. And the smallest eigenvalue, it will be the last one in the diagonal matrix. It will be the last one. That's why I will take the furthest, actually, eigenvector that's corresponding to that last one. Okay? Why we mentioned that this constraint? Because I told you earlier that if I'm telling you AX equal to 0 is a solution, is the problem that we need to solve, particularly X equal to 0 will be a solution, correct? But this is not an interesting solution. This is not what we are targeting. I would like to force X not to be 0. That's why I said like to be equal to something. But why I said it is equal to 1? Because we already also mentioned that if A of X is equal to 0, so the multiplication of X will give me the same exact solution. 5X will give a solution, 7X will give a solution, 8X will give a solution, but I need just like the unity solution. Just to force it, just like give me only 1. I don't need like all of this multiplication. That's why I force this will be X equal to 1. So I'm just repeating. So now we got to solve these eigenvectors, which means that I have now P's. Remember, this P1, P2, P3 is not points. This is just a vector. This P1 vector has P1, P2, P3, P4. This P2 has P3, P4. Do you remember the rows? I just showed you here. This is all of these. This is all of these. This is all of these. So by solving these 12 equations, I have been able to get all of these 12 unknowns. Okay, then. So we got the P. How we can move forward? Remember something, that this what we are trying to solve, yes? The poles, correct? Just going from one to the other. But also what we mentioned in the previous time, that when we would like to go from one to the other, we have intrinsic components and extrinsic components. So if I would like to go from the 3D world, I will go to the camera by extrinsic, and then from the camera to the 2D image framed by the intrinsic, yes? Now I can see like the extrinsic and the intrinsic per se. I can see the whole, the multiplication of the extrinsic multiplied by the intrinsic. This is what I got here from the P, correct? But this P, if you review the previous slides, this P actually came from other stuff, as I will remind you here. This comes from all of these things. P equal K multiplied by the rotation and translation, which translation is minus RC, if you recall. If you do this, K multiplied by R minus RC, K multiplied by R, I will call this M, K multiplied by minus RC, K multiplied by R is M, so it is minus MC. So now I have P is equal to that. My target right now, how to decompose this P to extrinsic component and the intrinsic component. I need to decompose that. How I can do that? First of all, I may think about find the camera matrix C. So if I were to ask you, what is the projection of the camera center? Where is exactly the projection of the camera center? If you think closely, actually, you will find that the camera center is the null space of the matrix P, which is P multiplied by C should be equal to 0. So basically, the projection of the camera center should be equal to 0, PC equal to 0. Then how we can get the camera center then? PC equal to 0. Same thing exactly as AX equal to 0. How we can solve AX equal to 0? X will be the eigenvectors, the smallest, or the eigenvectors corresponding to the smallest eigenvalue of the matrix A transpose A. Here's exactly the same things. SVD will do exactly the same things. C will be the eigenvector corresponding to the smallest eigenvalue. Okay, so now we got C. But we need now to get the K multiplied by R, because this is the M. I need, so C, I got it. But how about this? K and R. So C here I have it, but I need to get K and R to have like the whole exact idea or image. How we can get this intrinsic K and the rotation R? The question is, Do we know any information about the K and the R? Do you remember the K? I thought like, yeah. Do you remember the K? This was the K. This, by the way, called what? Right upper triangle matrix. This is called right upper triangle matrix. Means the upper triangle just like has value. The lower triangle doesn't have anything, it's just zeros. This matrix is called that way from linear algebra, by the way. It's not from me, this is from linear algebra. Okay, so now we know that K is a right upper triangle. What we know about R? We know about R that actually it is orthogonal. So now M is equal to an upper triangle matrix multiplied by orthogonal matrix. If you are strong in linear algebra, you will know that this is actually a QR decomposition. I can't review the QR decomposition, but it is a QR decomposition. If you would like actually to put a certain matrix by a multiplication between an upper triangle matrix and an orthogonal matrix, you can do that by QR decomposition, and then by this QR decomposition, then you can get from M the K and the R. Okay, so now we have solved this. We know now how to get the pose. We get everything. So what is the advantages? Very simple to formulate analytic solution. But is there basically a particular problem that we may face? Yes, we have something. Doesn't model any radial distortion as an example. If we were to have any radial distortion, it won't be able to do that, as we will see shortly. It is a little bit hard to impose some constraints. I can't, according to the equation that I have solved, I can't put like some constraints or impose some constraints. In addition, it is not minimizing the correct error function, and we'll see this shortly. How we can solve that? Now we need a nonlinear methods. So I have to define an error function, E, between the projected 3D points and the image position, which E is a nonlinear function now of intrinsic and extrinsics and also radial distortion. Oh, yeah, we do understand that, but we can't think about like how we can formulate that. Okay. Let's see first how I can get a radial distortion, and then we'll go to the math. So if you were to have the image, no distortion will look like that. But unfortunately, as you can see from this, you might get either a barrel distortion or cushion distortion as an example. So if you were to have an image like this, an image like this, and you would like to get the image corresponding X to X, do you think that everything will be correct according to the previous solution? Unfortunately not, because the previous solution assumed that everything is linear. But now I began to have like some non-linear relationship. Okay, so if I have non-linear relationship, I need to account a little bit into that. But from where is the error? Let's look at this. I have the point in the space P. And then I multiplied by a certain particular matrix, which is, as an example, M. I landed up here. However, the correct point that mapped to that particular point is called here UI and VI, or XI and YI, whatever the thing is. So there is a little bit of difference here. There is an error between what? Between the prediction that I had by multiplying M by P and the actual location, which is U and V. There is difference between these two. How I can get this difference? It's simply U is what I know, and then minus the location of this, and the location of this, as we already explained, I will multiply the M by P, which will be I, M1, P1, and so on, and divided by the last term. Yes, do you remember X divided by Z, Y divided by Z, or the upper row divided by the last row? When we get like to the inhomogeneous coordinate, apply the same exactly here. So U, because now I am in the image coordinate, minus this square plus V minus this square. Is that it? So this is just minimizing the reprojection error. But also, as I showed you in the previous slides, that you may have a radial distortion. With this radial distortion, I may even account for a little bit more stuff like 1 over lambda, which lambda can have like a nonlinear relationship like that, which called like the radial distortion. So ideally, X dash would be F of X multiplied by Z. Now I have to multiply this by Y over lambda in order to account for that. How this will reflect in the previous equation? It is U minus whatever I told you earlier, but I will multiply this by 1 over lambda. the same exactly this. This is as I showed you earlier, and then multiplied by 1 over lambda. So now I have added the distortions to projection errors and the radial also distortion. So I have everything right now. Then I will try like to solve something like this in order to get the correct image. So if you were to be given like an image as you can see here to the left, a lot of distortion, and then you apply the algorithm that I just showed you, this is what you get after. Yes, so change all of this kind of distortion. And this is, by the way, the experts in like in the image formation and so on, this is usually what they do, the photographer. If for any instance, like get anything here and there's a lot of like tools that can be used actually to enhance or work for removing all of these distortions. Another alternative multi-plane calibration, which is usually used now with this checkerboard. They will have like the checkerboard like this in many different positions, and then just take like images, and then we'll map again each of these images to the location in the image, and then you can easily calibrate your camera. And there is like a MATLAB version with open source codes that you can actually play with it, and also in OpenCV as well. But again, the disadvantage a little bit need to solve nonlinear optimization problem, unfortunately, with that particular also method. So just like to highlight that there are many different ways to calibrate a camera: radiometric calibration, color calibration, geometric calibration, noise calibration, lens and or aberration calibration. So a lot of calibration that you need actually to go through, and it will depend on what exactly you are interested in to calibrate that particular situation. So here I just like showed you a little bit of the projections of the matrices and how you can play with all of these kind of things, which ends up, by the way, later on to augmented reality. And if we were to show you this nice things, there is also another thing that I would like to highlight, which is called vanishing points and lines. What does that mean? I'm telling you that parallel lines in the world intersect in the image at a vanishing point. What does this exactly mean? Meaning that in the real life, I have this railroad. They will always parallel to each other, correct? But if you were to take an image, they are actually intersecting at a certain particular point, which is not true. But this is what you get from the image projection. This is not true, but this is what you will get from that. So if you were to think about this is the origin, and these are parallel lines in the real situation. In this image, when you do the projection, this will be projected to this, this will be projected to this, and then they will actually intersect at a certain particular point in that particular image projection. Interesting stuff. We have seen this a lot, but we never thought about it. So now, as we mentioned, parallel points will end up in the projection of the matrix intersecting at a vanishing point. So basically, the projections of parallel 3D lines intersect basically at a vanishing point. But also the projection of parallel 3D planes will intersect at a vanishing line. So if you were like to have two planes, yes, parallel to each other, they will intersect also in the projection, but in a line instead of in a point. Yes, in a line. If a set of parallel 3D lines are also parallel to a particular plane, their vanishing point will lie on the vanishing line of that particular plane. As you can see from here, this is vanishing line. Yes, if you have like an M2 parallel, they will intersect at this vanishing point, another will intersect at this vanishing point, but all of these will actually lie on the vanishing line. But however, not all lines that intersect are parallel. So this means that if I do see like intersections between two lines, that doesn't mean that always that's referred to a parallel line. Okay, so can we see like another examples for that? These are parallel lines, correct? You told us that parallel lines are intersecting, but we didn't see that intersection. You are lying. I'm not lying. They are intersecting, but the image is not like that huge in order to show you this vanishing point, where exactly they will vanish. Same thing with this parallel stuff. With this parallel stuff, they will also vanish at a certain particular later place and so on and so forth. How about these parallel lines? These parallel lines, the vanishing point at infinity. So we will not ever do that. But however, from all of these vanishing point, as you may see, all of these will intersect or lies in the vanishing line, as you can see here. So now we'll switch a gear to another new stuff, to view geometry. So just to recap from whatever we already mentioned so far, either for the homography or for the pose estimation, that we have a matches between 2 points or more points. We have matches between points in the 3D world and the image. And then we need to get the matrix P that relate this to that, correct? This is what we have solved it for so far. But now we are thinking about something else, which is called triangulation. What is that triangulation? Assuming that you are given these like matched point between x and x dash, but you also given p and p dash. Oh, so what then I need? I need the point 3dx. How we can get this 3D point x? Earlier, I gave you the point 3D point x and the small x in the image, and I ask you to get p. Now I'm not giving you that. I'm giving you this x in the image, and I'm giving you p, and I'm telling you where is that in the object. Where is exactly this in the world? How I can get this? I'm telling you also, like giving you 2 image poses. How we can solve for something like that. Okay, so we know that whatever the point that I had here in the 3D world, it should pass through a certain particular line that will contact x to the center of projection. So this means that I have to get the center of projection and then connect this C with the x, and I will have a line. Oh, okay, so now I understand that this is with this, I will have the line, but my point can land in any of these actually points inside the line. How I can get this in particular, for instance, just apply the pseudo inverse of P on X, then connect the 2 points. Okay, but how about these guys? Can we get any information from this? We will do exactly the same things. We will have the ray connected between the center of projection of the other camera, for instance, or the same camera which was in that particular location, as an example. And all of these are calibrated calibrated cameras. And then I should get like the intersection, but the question is, will these lines intersect? I guarantee that these lines intersect, that I have this and I have this. Should they always intersect? Hopefully, yes, in order to get that correct particular point ideally. But practically, there is errors, yes, and these lines might go like that, and this line also might go like that, but a little bit up or a little bit down, yes? So I may have like a little bit of a distance, and I will solve for what? Minimization again for that particular distance, and so on and so forth. I would like to get the best solution per se. So according to the noise, I might not get like a single solution, but we'll get the minimization. So again, given a set of noisy matches and the camera matrices, please get the 3D point X. So we formulate the problem now differently. I'm giving you 2 other parameters, and I'm asking for something else. How we can solve that? Okay, so we have X equal to PX. I may say like, okay, since it is a similarity relation, it involves the homogeneous coordinates and same ray direction, but differs by a scale factor, so I will add alpha, because it is in the same ray, still in the same ray, but I may apply just like a scale alpha. So basically X, Y, and Z, will equal to the matrix P as we already mentioned, multiplied by alpha will give me this. Okay, so nothing changed. I will do exactly as I did before. X, Y, and Z is equal to alpha. All of this I will call it the P1 transpose, P2 transpose, P3 transpose for each of these row. All of these I will call vector X. I will multiply this by this by that, this by that. I will write it here. Again, I have the matrix. So how we will solve for these unknowns in a similarity relation? Remove the scale factor, of course, convert to linear system, and solve with, again, singular value decomposition. But we would like to do like a little bit of a tricky stuff here before we do that, so just bear with me. I would like to remind you with the cross product and dot product before we move forward. A lot of interesting stories here. So with the cross product, if you recall, if I'm telling you that you have a B vector and A vector and then C vector, if you remember, if I will cross product P multiplied by A, it will give me another vector which is perpendicular to the plane that has the A and B. So it will be perpendicular for each of these vectors. It will be perpendicular to B and perpendicular to A as well. And the same apply if I do this between C and B, it will give me A, which will be perpendicular to all of these, and so on, or whatever like the vector at that time. So if I multiply two cross product between two vectors, the third one will be perpendicular to both of them. Okay, this is like geometry in the geometric domain, or geometric speaking. How about algebraic equations? Because we like equations. Because we work with the equations, yes? How we can do that? A multiplied by B is equal to this, this, and that. How we got that? If you recall, A is equal to I multiply AX plus J AY plus K AZ. The same apply for the BI, BX, and so on and so forth. Okay, so we put this in the matrix. A multiplied by B, I, J, K, AX, AY, AZ, BX, BY, BZ. So here they just call it 3 and 2 and 1, which one refer to the A1 refer to AX, A2 refers to AY, A3 refers to AZ. But I prefer to write AX, B, AX, AY, AZ, just like to remind you with the math that you already taken a while ago. Having this, if I would like to get the solution, if you recall, we get this one and then remove the line on the column, and then it will be I multiplied by the determinant of these matrices, which is AY multiplied by BZ minus AZ multiplied by BY. If you map the Y onto 2 and the Z to 3, you will find exactly that first row. AY, A2, BZ, it is B3, minus AZ multiplied by BY. AZ means A3, so it is A3. BY, Y means 2, it is B2, correct? Then we will go to this one, and then we'll remove that, and then multiply this by this, and this by this. However, with this one, I carry the negative sign, if you recall again and again. So please go and review the cross product. I just gave you here a hint, and believe me, this is what you will exactly get by the cross multiplication or cross product. Okay, so this is A, B multiplied by, or cross product by A will give me C. But if I will multiply B by itself, or A by itself, or C by itself, what is the exact solution? 0. Because if you recall also, A cross product B is A, B sine theta, correct? And if it is the same vector, so theta is 0 and sine 0 is 0. And that's why you will get the cross product is equal to 0. This is for the cross product. How about the dot product? The dot product, if we recall, A dot product B is A magnitude, B magnitude, cosine theta. So if the two vectors are perpendicular, theta is 90, so cosine 90 is 0. So basically the cross product between two perpendicular vectors is 0. So cross product between the same vector is 0. Dot product between perpendicular vectors are zeros, as you can see from here. So I'm telling you all of this. All of these is just review. Why? To know how we will continue the previous stuff, which was that I have x equal px or x equal to alpha px, and I would like to do a cross product between this and this. What do you expect that to be? The answer is 0, but why? I just told you earlier that if it is the same exact vector, or if it is like a scaled vector, scaled version of that particular vector, the cross product will give you 0. And I'm telling you here that x, and just like p multiplied by x, they are equal. So x multiplied by that is basically equal to 0. The cross product of two vectors, same direction is 0. So now I have something. So go back to the same equation. I would like to do this x multiplied by this px and equate that to 0. If you do this multiplication according to the same exact way I told you and I explained here, you will end up with this. You can do the math, but I don't want to spend a lot of time doing all of this, but it will be exactly the same. Believe me, if you do it, you will find that particular matrix according to that particular solution that we already agreed on. And this will be equal to 0. There is a little bit of a trick here that I would like also to highlight from linear algebra. This third row is a combination between the first row and the second row. What does that mean in linear algebra? Meaning that now I have only two important information from that particular matrix. In another sense, if I'm telling you that you have 3 rows, so you have to get 3 equations, but one of them actually depends on the other, so actually what I am getting really is just 2 equations. So the rank of the matrix will drop from 3 to 2. Why? Because a matrix of rank 3, meaning that I have 3 independent information. I have an equation, 2x plus 3y equals something, then another equation, 3x plus 5y equal another thing, and then a third equation, which is 7y plus whatever is equal to a new thing. However, in order to be rank 3, all of these equations will not depend on each other. But if I were to give you 2 equations and the third is just a conclusion or a direct multiplication of any of these equations, so what? I don't have any new information to solve this third variable, for instance. So this is just 2 variables because the third does not have any effect. And if you look closely at this, x times the first line plus y times the second line will give you the third one, rank 2 matrix. So now I need to solve these 2 equations only. That's why you have seen like I have already like the one there. There is no need for the z. I just need 2 equations from that, solve these 2 equations. Then again, a multiplied by x equal to 0. Go back to here. Plug this by that. It will give you from that. If you decompose that, it will give you this. So this, it will give you that. Again, ax equal to z. So now we can make a system of linear equations, 2 lines for each these 2D point correspondence. How do you solve this homogeneous linear system? SVD. Yes? Here more linear algebra than the linear algebra course itself. Yeah? But here's the application. Now we see how we can apply all of these things by the singular value decomposition. And as we mentioned earlier, singular value decomposition, minimize this, given that it is the eigenvector corresponding to the smallest eigenvalue of this particular matrix.